Thanks. First, before I start, thanks to the organizers for inviting me and for giving me the chance to talk a bit about my work here. And my plan is to talk about Fusion 2 categories. Now, we defined these Fusion 2 categories in a paper with Chris Douglas, which is now sort of about 1.5 years ago. And the original motivation for this paper essentially comes from quantum topology. So the question, the perspective from quantum topology that I want to advocate here, or that we sort of take in this paper at least, is that it's about constructing linear algebraic manifold invariants via things which you could call state sums. And basically the slogan is, take some appropriate linear algebraic data and contract it, like really tensor contract it according to some finite combinatorial presentation of a manifold. And this finite combinatorial presentation could be a triangulation of the manifold. Can you all hear me, or is there a problem with the audio?
I think I heard you pretty well.
I can hear you fine.
Yeah.
Okay. So maybe it's just you, Shenchang. But yeah, if there's a problem with the audio, I think it has happened before that there was a problem with my audio. Please just tell me, then I'll wear my headphones, then it should be better. But it's also a bit uncomfortable. So okay. And so the slogan is, take certain linear algebraic data and contract it along this presentation of your manifold. And the big question then, of course, is what algebraic data should I take? And the situation in 3 dimensions was sort of sorted out in the 90s, basically. And sort of the names attached to this are usually Reutter and Barrett-Westbury. And the idea there is that they can take something which is called a spherical fusion category, and we've seen fusion categories before this week, and turn it into an oriented 3-manifold invariant. And in 4 dimensions, the situation up to this paper was a bit chaotic. And we had sort of several state sum-like constructions, just to name a few, coming from, for example, braided fusion categories or G-cross braided fusion categories, 2 groups, and so on. So there was sort of a variety of constructions. And what we really set out to do is to figure out a good notion of Fusion 2 category and a state sum construction for spherical Fusion 2 categories, which give me oriented 4-manifold invariants and which sort of unify and generalize these constructions. So that was sort of the setup, the start. And of course, sort of seeing this topological perspective, we're now seeing Fusion 2 categories or variants of these Fusion 2 categories, and of course higher fusion categories appearing in the classification of topological orders, and maybe to sort of really flag up is this paper here, which proposes a higher dimensional generalization, and which in dimension 2, I think very likely matches up. It's not, I mean, I don't have a proof at the moment, but it looks sort of, the definitions look similar enough so that it's likely that they actually sort of lead to the same notion of Fusion 2 category. Right. What I want to talk about then in the next 45 minutes is maybe not the topological perspective, but really more the algebraic side. So how can we think about Fusion 2 categories? How are they similar to Fusion 1 categories? How are they different to Fusion 1 categories? How to sort of work with them? And for that, let me just sort of go back and tell you how Fusion 2 categories are defined and how to work with them. So first of all, in whatever I'm going to talk about now, I fix some field K, and I assume it's algebraically closed and of characteristic 0, so just take it to be the complex numbers if you like. And this is sort of our basic setup. Let's just sort of go back and think about what a fusion category is. Now, the way we've sort of seen fusion categories presented this week is to say, well, we have a finite set of particle types, and we have certain fusion rules, and we have certain F symbols. But to categorify, it's better to go to a sort of basis-independent perspective on these, and that I think we've also seen is that a multi-fusion category is basically the same as a K-linear, finite semisimple, monoidal category with duals. So let me sort of immediately flag up that K-linearity is structure on a category. I really give all the morphism spaces a vector space structure. And the monoidal structure is structure. Finite semisimplicity is a property of K-linear categories, and having duals is a property of a monoidal category. And then being fusion is just the additional restriction that the tensor unit is simple. And so later on, I mean, again, this will be sort of an easy additional restriction to go from multi-fusion 2 categories to Fusion 2 categories. Okay, now to categorify fusion categories, we should therefore first categorify what finite semisimplicity means. So K-linear two category is easy, but what is finite semisimplicity? What's like a good categorification of finite semisimplicity? And this gives sort of rise to a certain heuristic that I want to sort of very briefly talk about. I don't want to go into too much details, but it sort of motivates the definition that I'm going to give. And the heuristic essentially starts, if you want, from a structure theorem, which tells me that if I have a finite semisimple K-linear category, well, essentially, it's just a copy of n powers of the category of vector spaces, of finite dimensional vector spaces. So this is my finite set of particle types, which determines the semisimple structure. And so really, one should think of sort of from this heuristical perspective, one should really think of a finite semisimple K-linear category as categorifying a finite dimensional vector space. This is sort of analogous to the structure theorem for finite dimensional vector spaces. Every vector space is isomorphic to C to the n. Now, there's of course a much deeper reason why we should think of finite semisimple K-linear categories as categorifying finite dimensional vector spaces. It's not going to be super important for this talk, but I'll say it for those of you who are sort of from a higher categorical perspective or aware of the cobordism hypothesis. And this is that all proposed candidates for a symmetric monoidal two category of all two vector spaces. So if I just look at all two vector spaces, there are a bunch of candidate definitions of what this could be. For example, something like K algebras and bimodule maps, or K linear categories and bimodule functors between them. And all or most of these proposed candidates have the same fully dualizable subcategories. So if I really want to sort of carve out what it means in them to be finite, I'll end up with the same notion. And this notion is always this particular symmetric monoidal two category we're seeing here, which has sort of two important different presentations. And one of them is saying it's the two category of finite dimensional Semisimple algebras, finite dimensional bimodules and bimodule maps. And the other is to say it's finite semisimple K-linear categories, K-linear functors and natural transformations. And to pass from the left side to the right side, I take the category of modules of such a semisimple algebra. And so then this leads to the following sort of heuristic table. I start with one vector space, it's just a finite dimensional vector space in linear maps. I look at certain algebra objects in them, which gives me the two category of finite semisimple algebras, bimodules and bimodule maps, which I can alternatively think of as finite semisimple categories, functors and natural transformations. Now again, to get to multifusion categories, what I do is I look at the monoidal category object in there, which has duals, right? Because recall a multifusion category is a semisimple category with a monoidal structure, which is duals, and so on. So this already suggests a sort of approach to sort of continue and to categorify. And so let's go into sort of a bit more detail of what we need to do.
I'm sorry, I forgot again. Could you share the PDF?
Yeah, give me a second. This should work, right? If I just drop it in the chat. Unfortunately, it's a GoodNotes file, which means it's a really large PDF. Okay, so let's continue. So let's look a bit more closely at what we're doing here. Basically, what we're seeing here, we take certain appropriate algebra objects, end up here, pass to this other side, and again take algebra objects. So since this is an equivalence, we might have taken algebra objects just sort of on this side. And this is essentially similar to the approach that Theo Johnson-Frade and David Gaiotto take in their condensation paper. But what happens if you sort of take the standard definition of multifusion categories, that before you take algebra objects, you sort of pass to this side of the equivalence. Now, of course, sort of categorically, it will lead to the same to the same category of three vector spaces, because again, this is an equivalence. But there's a big difference. Namely, let's sort of look at this more closely. Namely, if I would take a monoidal category object in here, what I would end up with is having an algebra A and then a bimodule which goes from A tensor A to A. So the monoidal structure would suddenly be a bimodule of algebras. And then all of these things become much, much, much harder to work with. So what this equivalence is doing, it essentially tells you or allows you to reinterpret your bimodules as functors. So that then at this end, if I want to build a multifusion category, it's actually a monoidal category and not some sort of a pair of bimodule together with a bimodule, an algebra together with a bimodule from A tensor A to A and so So this really gives it sort of a more common, a more categorical perspective. And this is essentially what's known as the Imagevats theorem, which tells me functors are represented by bimatrix and vice versa. And basically the desiderata to get a notion of what a semisimple 2 category should be is precisely aiming for such an Imagevats theorem. So this is our desiderata. We want to be able to say, well, on the left, I have multi-fusion categories, I have finite semisimple bimetry categories, bimetry functors, natural transformation. I want to be able to say, if I take modules, I end up somewhere which is in semisimple 2 categories, k-linear functors, natural transformations, modifications. And I want to have some characterization of what it means to be a semisimple 2 category, what it means to be sort of the form mod of a multi-fusion category. If you want sort of an external characterization of that, without just saying it's mod of a multi-fusion category. And once we have that, we can just say, well, a fusion 2 category or multi-fusion 2 category is essentially just a monoidal 2 category whose underlying 2 category is semisimple. And then we're sort of in business and have sort of duals. And this is what we're going to do. So this is really the main part, if you want, of this talk. Okay, so let's look at the definition. And again, if you haven't seen the definitions of what a semisimple,
you don't need over here the 2 categories to be linear before you need it to be.
Yeah, exactly. Yes. So all my categories that appear in here are linear. So this is a semisimple k-linear 2 category.
Oh, okay.
And I'm going to give all of the definitions. So if you haven't seen the definition of what a semisimple category is, or if you haven't seen the definition of a fusion category in this perspective, I'll structure this talk so that I give the definitions for n equal 1 and n equal 2 in parallel, so that one really sees where these two notions are similar, where they're different, and sort of how they match up, and how sort of certain notions of things appearing on one side sort of appear on the other side. So, right, so let's look at the definition. Again, here I'm going to give this definition for 1 and 2 in parallel. So semisimple n category for n 1 or 2 is a k-linear n category such that, so let's look at the definition. Semisimple 1 category is a k-linear 1 category which is direct sums, which is idempotent complete, and such that for every object A, the endomorphisms form a finite dimensional semisimple algebra. Now there are many definitions of the semisimple 1 category, they're all equivalent, and they all look a bit different. This one is a very convenient one to categorify. I think it nicely fits into this hierarchy of notions that we've seen before. And so then to categorify, well, we're basically asking it to have direct sums to be 2 idempotent complete, whatever that's going to mean, and such that for every object A, the endomorphisms of that object form a multi-fusion category. So this last condition, you can think of as really encoding semisimplicity. This is what tells you that the thing is semisimple. This is it is semisimple on Hom categories, whereas this is saying it is semisimple on Hom vector spaces. And these two conditions are completeness conditions. So this is what guarantees me this Imagevats theorem. This is what guarantees me that I can translate bimodules into functors and vice versa. So that's what's going to be important for the Imagevats theorem. It's not really about semisimplicity per se, but it's really sort of more about the completeness, and this is a sense of Kurobi completeness. Now, I'm not going to talk about direct sums. They are defined as you would expect, so those are not too hard to define in a higher categorical setting. What is sort of new and interesting is what the appropriate notion of idempotent completeness is, and that's somehow really part of the heart of the story. And so this gets me to the notion of 2 idempotent completeness. And this is also sort of an interesting history. This in n equal 2, we talked about this in this paper, and then it was generalized to arbitrary n, was sort of slightly changed, and that allowed them to generalize it to arbitrary n by Reutter and Johnson-Fried. And I'm going to talk a bit more about the comparison to this. And it's also very closely related to various ideas that have been around and have sort of appeared, and here's sort of just sort of a random subset of these ideas that I'm aware of. There's work by Liang and Kong on condensation algebras. Kakabel, Runkel, Sharman have a setting, sort of in the oriented setting, where they talk about these completeness conditions, and Morris and Walker also have unpublished work on this. And a rough idea, and I think I expect we're going to see this some more in later talk, in one of these afternoon talks by Theo Johnson-Fried, is that we can categorify idempotence in 1 categories to separable algebras in 2 categories. Now, I don't want to give too much intuition about this idea, because again, I expect it to come up again, and because I want to get to the definition of what a fusion 2 category is. But let me just tell you actually the definitions of these things that we're seeing here. So let's briefly recall an idempotent. So if I have one category, what's an idempotent in that one category? Well, it's just some endomorphism P that squares to itself, right? And if you know string diagrams for categories, you can think of this as sort of little dots, such that if I take 2 of these little dots next to one another, I get a single little dot. Now, closely related to the notion of an idempotent is the notion of a section retraction pair. This is just a pair of morphisms F and G, such that they compose in one direction to the identity. So this is the identity, but composing them the other way around is not the identity. And we say that idempotents split if for every idempotent there exists a section retraction pair, such that sort of composing them the other way around gives me the idempotent. So in terms of these pictures, if every idempotent I can actually write as a composite like this, right? And this is really gives you sort of a visceral sense of this idempotent splitting apart into sort of 2 dots and a little line between them. And then finally, I say that my one category is idempotent complete if every idempotent splits. And this is sort of completely standard definition that has been around for many, many years. And so then let's see how to categorify this. Let's sort of completely in parallel categorify these notions that we're seeing here. So I start with a 2 category. What I assume of this 2 category to make my life a bit simpler is that it's locally idempotent complete. So in other words, that all the HOM 1 categories that I'm seeing here are already idempotent complete in this one categorical sense. So I can already split idempotents up there. Let's sort of look at the basic players. Here we had talked about idempotent. So what's the categorification of idempotent that I'm using here? It's the notion of a separable monad. Essentially what a separable monad is, let me actually also get the pictures up. A separable monad is a unital algebra object P in the endomorphism category of some object B, whose multiplication admits a section as a PP bimodular map. Sort of the definition, or way to sort of see this condition in pictures, again in sort of the string diagrammatic calculus. Now we're in the 2 category, so we're drawing these planar pictures. We have some object B, and we're saying in the monoidal category, which just happens on this object B in HOM VB, we're looking at this unital algebra. So I have my multiplication here, and I have a unit here. And asking this to be separable means that there exists something like a co-multiplication here, fulfilling this Frobenius-like relation and this specialness relation. So another name you can give a separable monad is something like a non-co-unital special Frobenius algebra, if you're sort of more familiar with that terminology. And so now we've talked about idempotent. What's the analogous notion of a section retraction pair that we're using here? This is what we call, or what is called, a separable adjunction. So separable adjunction is an adjunction whose co-unit admits a section. What does that mean again in pictures? It's an adjunction, so we have sort of a right-turning wire and a left-turn, and another right-turning wire in the other direction, which fulfill the adjunction equations, so these sort of snake equations that most of you will be familiar with, such that there exists one of these splittings. So there exists a map like this, such that I can fulfill this equation. And now a separable monad splits if I can glue it together from a separable adjunction. So the separable monad splits if there exists a separable adjunction and an isomorphism of monads, right? If I have an adjunction, I can sort of take F and G, compose them together in a particular order, and this gives me a monad, and I just require this monad to be isomorphic to my original monad. Again, the pictures are maybe a bit more insightful. It's basically saying that this monad that we're looking at here really arises as sort of a pair of pants monad in my 2 category, really arises as this pair of pants algebra. And so again, we really sort of viscerally see the sense in which this monad splits apart. Really this sort of algebra structure that I'm seeing here is sort of a shadow of this adjunction. And we say that the 2 category is 2 idempotent complete if it is locally idempotent complete and if every separable monad splits. So whenever I have a separable monad in my 2 category, I'll actually recognize that it comes from such an adjunction. So I can always replace, so to say, this monad here by this new object that it actually wants to encode, right? Similar to idempotent completeness. So really sort of split these things apart. Okay, so that's the definition. And let me make some comments about this definition. First of all, something which is maybe a bit of a more technical comment, but is quite relevant, is that there's sort of a slight mismatch between the notion up here and the notion down here. And I think this was really quite nicely clarified in Theo and David's paper. Namely, down here, I require unitality of this monad. So I say here this is an algebra with a unit. We don't really see something like a unit for this idempotent, right? We have an equality between p squared and p that corresponds to the multiplication, the map which goes from p squared to p for the monad. But we don't really have a map from 1 to p, because that would just say, oh, I have an equality between 1 and p. And indeed, in this condensation paper, what essentially happens is that Davide and Theo consider a non-unital version of the story, where idempotents and these non-unital versions of separable monads really then look the same and are sort of categorically the same, just in different dimensions, and that allows them to categorify this further and get sort of an arbitrarily dimensional version of two idempotent or n idempotent complete or condensation complete. And as a comment, and this is also proven in that paper, is if C is locally idempotent complete and has adjoints for one morphisms, these two notions of idempotent completeness agree. So depending on which one you're more familiar with, sort of, you can use whichever you like in the setting that we're working in here. Okay. Now, as you may well know, is every one category can be completed to an idempotent complete one category. So I can sort of always assume I just pass to this larger world where I am idempotent complete. And similarly, every locally idempotent complete two category, C, can be completed to two idempotent complete two category. And explicitly what this construction is doing, it takes the two category of separable monads in C, bimodules in C, and bimodule maps in C. And moreover, if C was already two idempotent complete, then the sort of canonical map you get is an equivalence. So this is really an idempotent operation itself. You pass, so once into idempotent complete, I'll always be two idempotent complete. And so really, you should think of this sort of from the outside, really just as a categorification of idempotent completeness, and it really behaves very, very similar. Okay, any questions up to this point? Yes.
I have a question, or actually I have a comment for the audience.
Yes.
Which is that I never actually thought through if it was possible to have both a unit and a co-unit.
Yeah.
And I sort of would love to hear if somebody can sort of find out if there's kind of a similar state. Like we proved that kind of under some conditions, David's definition that requires a unit is this sort of equivalent to ours. You can always force your things to have units, and I don't know if you can force it to be both at the same time.
Exactly. There's maybe sort of a comment on that comment that's interesting is the notion of bimodules. Sort of our bimodules are just unital bimodules, so they are bimodules for this algebra and they respect the units. And Theo's and David's bimodules are bimodules both for the multiplication and the co-multiplication, which is part of this data. So there's sort of there seems to be a trade-off between considering the co-multiplication as part of the data or considering the unit as part of the data. And I really don't, I'm not sure how sort of the co-unit fits into that story. So I agree. So definitely neither here nor in this other story is a co-unit.
Well, some people in the audience should solve this.
Yeah, exactly. Okay, so, right. But now sort of having this set up, we can define what it means for a two category, for K-linear two category to be semisimple. And we've already seen the definition a few slides back, but let's just sort of recall it again. I said that the two category is semisimple. If it has direct sums, it is two idempotent complete in the sense that I've just talked about, so if the separable algebra splits. And the endomorphisms of every object form a multifusion category. So that's sort of a sort of straightforward definition then. And okay, so here's the definition. Let's sort of look at what this means, right? Let's look at examples and let's sort of get a bit of a feeling of the structure here. So first of all, in a semisimple two category, what you would expect is a notion of an object being simple, right? I've just said that all these Hom categories are semisimple. So there I have my simple one morphisms and so on. I have my decompositions. But what about objects? So here's a definition proposition. An object X in one of these semisimple two categories, I define to be simple if one of the following equivalent conditions holds. So there's sort of a variety of ways to say when an object is simple, similar to the one categorical case, of course. And again, this definition proposition is sort of works in dimension 1 and in dimension 2 to again sort of contrast it quite nicely. So just sort of the historical one is to say an object is simple if every sub-object is either 0 on equivalence. Alternatively, you could say an object in a semisimple k-linear category or 2 category is simple if it's indecomposable under direct sums. Or if, I mean, in this case that we're working with an algebraically closed field, as I said, we're doing, an object in n=1 case is simple if its endomorphisms are just a unit ring. And in our setting, an object is simple if and only if the endomorphisms of the identity 1 morphisms, so the endomorphism 2 morphisms of the identity 1 morphisms, which is now again just an algebra, is the ground field. So this is the notion of simplicity. And then indeed, maybe one sort of final definition is that we say that a semisimple 2 category is finite if it has finitely many equivalence classes of simple objects. So again, similar to the n=1 setting. Okay, and then maybe as you would expect, every object in a semisimple 2 category decomposes uniquely up to permutations of summands and equivalences into a direct sum of simple objects. So really, again, the simple objects, similar to the n=1 case, really govern what's going on in these semisimple 2 categories. Okay, and now sort of it looks like semisimple 2 categories behave very much like semisimple 1 categories. And that is only true up to this point. So now we're sort of starting to see these things structurally diverging. Because the next thing you could ask for is there something like a Schur's lemma? Right? In a semisimple 1 category, if I have 2 simple objects, they're either isomorphic or there's no non-zero morphism between them. So you could ask, is there something like Schur's lemma? And the answer is no, there's no Schur's lemma. And so let's look sort of zoom out a bit and let's look structurally at how this thing looks like. Namely, the closest thing I have to Schur's lemma is that if I look at non-zero 1 morphisms between simplers, they have a sort of 2 out of 3 properties. So if 2 out of fg and f composed g are non-zero, then the third is. So sort of non-zeroness is transitive, if you want. And this sort of allows me to come up with the following structural perspective. Whereas in dimension for semisimple 1 categories, essentially what I'm looking at is sort of a collection of simple objects. All of them have sort of endomorphisms k. So really what I'm looking at is just a finite set. What I'm seeing here now is, okay, let's just sort of arrange what we're seeing. We take sort of, I draw a point for every simple object. Now I can ask, if I have 2 simple objects like this and this, is there a non-zero 1 morphism between them or not? Sometimes there is one like here, and sometimes there's none like here. And in fact, this gives me a certain equivalence relation, or sort of coarse graining, if you want, on these simple objects, according to whether they're in the same component, if they have non-zero marks between them or not. And this relation up here is telling me that if I'm in one component, then definitely all of them have a non-zero morphism between them. And if I'm in different components, then none of them will have a non-zero morphism between them. So this is sort of then structurally how the semisimple 2 categories start to look like. There exists a non-zero morphism between any 2 objects in the same component, and there exist no non-zero morphisms between any 2 objects in different components. So I do have these components, and I can sort of move from one to the other only in one component. And then again, from our conditions that we've been seeing, the simple objects themselves, the endomorphism 1 categories, by definition are first of all a multi-fusion category. But in fact, since this object is simple, this means that the endomorphisms of the identity 1 morphism are one-dimensional. This implies that these endomorphism Hom categories are actually fusion categories. So what we're sort of structurally seeing here is sort of the structure where at every dot there sits a fusion category. Between these dots, we have this Hom category, which is acted on by the left by this fusion category and on the right by this fusion category, just by composition. So this gives me some non-zero indecomposable bimodule category. And so I'm getting sort of these little blocks, which have this interesting behavior, and they don't really talk to each other. So there's a certain sense in which it's similar to a semisimple 1 category, only that now previously sort of the blocks had a single point in it and no interesting behavior at all. And now the points essentially encode the data, if you want, of a single fusion category. And these are the Reutter equivalent fusion categories and how they're sort of connected up. So then if you look at this structure, basically there's something you already can if you're familiar a bit with multi-fusion categories, you can already see here. And this is essentially that the data that this a collection like this encodes is essentially the data of a multi-fusion category. So you can say every block corresponds to, a multi-fusion category can break up into a direct sum of multi-fusion categories. So this is somehow the block decomposition. And if I have an indecomposable multi-fusion category, essentially it encodes what happens in one block. And this leads to the following theorem. A k-linear n category is finite semisimple. And this again works for n equal 1 and n equal 2. If and only if it is equivalent to an n equal 1 finite dimensional modules of a finite dimensional semisimple algebra, and an n equal 2 finite semisimple modular categories of a multi-fusion category. So this notion of finite semisimple k-linear category that we've defined before, having direct sums, being two idempotent complete, and being locally finite semisimple, implies or is equivalent to saying I'm finite semisimple modules of a multi-fusion category. Right, conversely, finite semisimple modules of any multi-fusion category is a finite semisimple 2 category. And I've just seen a question in the chat whether the dot here means that it's a simple object, and this is absolutely correct. So the dots here mean they stand for simple objects. Yeah. And more generally, we get what we were aiming for, this desiderata, the semisimple Einberg-Watts theorem, which tells us that if A and B are multi-fusion categories, I can look at the 2 category of finite semisimple A, B bimodular categories, bimodular functors and natural transformations. And this is in fact equivalent to the 2 category of k-linear functors from mod A to mod B transformations and modifications. So moreover, more than this, I also get the statement that bimodular categories turn into functors. And now I'm in business, right? This is what we were hoping to get, because now I can say, well, now my multi-fusion 2 category is essentially just a monoidal 2 category whose underlying, a monoidal 2 category whose underlying 2 category is finite semisimple. So this is now what I can later define, but maybe before I make this definition, let me give some more examples of finite semisimple 2 categories. Of course, I don't really need to give you examples because I've already told you all examples. It's just finite semisimple module categories of a multi-fusion category, but it's still interesting to look at some. So the primordial example of a finite semisimple 2 category is, of course, 2-vec, 2 category of finite semisimple k-linear categories, k-linear functors, and natural transformations, or equivalently, algebras, bimodules, and bimodules map that we've seen before. And in this heuristic structural perspective, what we're looking at here is a single component with a single simple object and the endomorphisms of the simple object being vectored. Another example is modules of a fusion category. Modules of a fusion category are precisely the finite semisimple 2 categories which have a single block. And conversely, if I have one of these single blocks, right, I just take one of the endomorphism fusion categories and I can recover this block as modules of that fusion category. So there's all of these fusion categories which sit as the endomorphisms of these things. They're all Morita equivalent, and they all give rise to the same semisimple 2 categories. So the one block semisimple 2 categories, so to say, correspond to fusion categories. And slightly different thing then is you can also look at representation categories of homotopy finite 2 types, or also known as finite 2 groupoids. So if I have a finite 2 groupoid, I can look at functors from this finite 2 groupoid into 2-vect, and this again forms a semisimple 2 category. And these examples are also they are similar to how representations of groups or of 1 groupoids more generally form semisimple 1 categories. Okay, so let's then finally talk about fusion 2 categories. Maybe at this point, are there any questions right now? Okay, so as I said before, now that we have this notion of semisimple 2 category, which fulfills this Einberg-Watts-like theorem, we can define fusion 2 categories or multi-fusion 2 categories just as we would define them, namely for n equal 1 or 2, I define a multi-fusion n category as a monoidal k-linear n category with the property that first the underlying k-linear n category is finite semisimple in the sense that I defined before, and every object has a right and a left dual, right? and that's it. That's the definition. And a fusion n category is a multi-fusion n category in which the tensor unit is simple. So it's really sort of very standard. Maybe one comment I should make is that in the notion of what it means to be a semi-simple 2 category, it's already entailed that every one morphism has an adjoint. Because I'm explicitly asking I'm explicitly asking this 2 category to be locally semi-simple, and I'm asking the endomorphisms of every object to be a multi-fusion category. And in a multi-fusion category, you already assume that every object, and in this case, so one morphism has a dual. So everything has adjoints and everything has direct sums in these gadgets. Okay, so that's the definition. Let's look at some more examples. And again, let's look at sort of these examples in parallel between the case n equal 1, which you might be familiar with, and the case n equal 2. So the first sort of simplest example is I can take in n equal 1, I can take the modules, the finite dimensional modules of some commutative semi-simple algebra. So I should say semi-simple algebra here. That is always a multi-fusion category. And it's fusion if and only if the algebra is one-dimensional. So it's a bit boring. Similarly, I can take the modules of some braided multi-fusion category. And this is fusion if and only if this braided multi-fusion category is actually a fusion category. So modules of a braided fusion category form fusion 2 categories. And in fact, we can say a bit more, namely a fusion 2 category has a single component, right? So we've looked at these pictures before, if and only if it's mod of a braided fusion category. Essentially, this comes from take this single component, the tensor unit is going to be in the simple component, in the single component, you just take the endomorphism fusion category of the tensor unit, which is going to be a braided fusion category, which determines the whole thing. And other examples then to look at is now sort of representation categories and G-graded vector space categories, essentially. So let's do them in order. If I have a finite one cuboid X, I can look at the representations of this finite one cuboid. So in other words, what is this? This is functors from this one cuboid into the category of vector spaces. And this category is a fusion category if and only if this finite one cuboid actually just has a single object. So if pi0x is a point, so if X is really just the delooping of some group. And then it's just a representation category of that group, which is sort of well known to be a fusion category. Similarly, if I take a finite 2 cuboid X, I can take representations of this finite 2 cuboid. Again, this is just functors from X now into 2 vect. That's a multi-fusion 2 category, and it's fusion if and only if this finite 2 cuboid has just one point. So if it's the delooping of a 2 group. Now this is sort of the red part, and these 2 categories are actually symmetric monoidal, as in the n equal 1 case. Conversely, we can do sort of the G-graded vector space version of the story. I can start with a finite 2 group, so finite 2 group being defined as a monoidal group like finite 1 cuboid.
If x0 is not a point, or pi0 is not a point, what will go wrong?
If pi0 is not a point, it just decomposes as a direct sum of things.
Direct sum, okay.
Because right, there's no, like if pi0 is not a point, then you can just write X as a disjoint union, and this disjoint union structure translates into just a direct sum decomposition of this category. And the direct sum of multi-fusion or fusion categories is never a fusion category, right?
Okay.
And right, and if I start with a finite, it's still multi-fusion, right? It's just this fusion condition, the simpleness of the unit you don't get. If I start with a finite 2 group, so this is this monoidal group like finite groupoid, or in other words, if you deloop it, you could also define it as a connected 3 type, homotopy 3 type, if you're sort of more familiar with that perspective. Then I can take vec-G, which are again sort of as a semi-simple 2 category, is again defined in the same way. So it's just functions, in this case functors from G into vec-K. What I'm doing here is I completely forget the monoidal structure when I'm doing this. I really just take the underlying 1 groupoid of G. And similarly here, I can start with a finite 3 group and take functors from G into 2 vect. And this inherits another monoidal structure, which now comes from G, which now comes from the monoidal structure that I haven't yet used up in G. right? Because to define the semisimple 2 category, I don't use it. Here I use sort of the full categorical structure of this group, or I should even talk about functors. So this is this additional monoidal structure coming from G. And again, this gives me multifusion 2 categories or multifusion 1 categories, which are in this case fusion. This is fusion if pi 1 of this monoidal group like finite groupoid is trivial. So if this finite groupoid actually doesn't have any morphisms, so if it's just a set. And then again, what we're seeing here is the usual story that this G is just a group. And this is fusion if pi 2 of G is trivial. So it's sort of funny that this is, in some sense, these are flipped over versions of these guys, if you want. One of them requires the highest homotopy group to be trivial, the other one requires the lowest homotopy group to be trivial to get a sort of fusion structure. And they can be twisted by 3 cocycles here, as you might well know, and similarly these can be twisted by 4 cocycles, and this really means 4 cocycles in a homotropical sense, that I take this finite 3 groupoid, I can deloop it to give me some 3 type, and then I just really take the 4th cohomology of this 3 type. And maybe to end on a concrete example then, I might actually have enough. Yeah, let's try to end on this example and then I'll see how much time I have left. Let's really, again, sort of look at this example, which here, unfortunately, I didn't give a name, so I should probably write here. I'm building a thing which I call, sorry, this is of course vect G omega, and this is 2 vect G omega. So let's sort of look a bit more at this 2 vect G omega, how this looks like. I have my G, which is a finite 3 group, and I have this 4 cocycle. And you can show that, right, you already know that pi 2 of G has to be trivial such that it's fusion. And you can show that the number of components of this multifusion 2 category, so the number of these blocks, is pi 0 of G. So let's sort of look at the specific case where I assume it's fusion. And I assume it only has 1 component, just to make our lives a bit simpler. So this means that actually pi 2 of G is trivial and pi 0 of G is trivial, so there's only a pi 1. So I immediately know that G is of the form a Ka1. So it's just, again, you have some abelian group, because this itself can be delooped. This itself has a monoidal structure, so it's some abelian group, and you deloop it once. And we've also seen before that if I have a single component, I'm actually mod of a braided fusion category. So let's sort of try to see what braided fusion category this corresponds to and how these things sort of relate to one another. So here I have 2 vect Ka1 omega, and I claim actually this is the same as modules of vect A omega in this case. And how does this even make sense? How does this type check, right? Why can I use omega here and omega here at the same time? Well, because these 2 omegas, well, omega is just this 4 cocycle, which now is for the space, which is the delooping of G, which is in this case a Ka2. This classifies twists of these sort of braided 2 vector spaces, as we've seen above. And they also classify braided monoidal structures on vect A, where vect A is just a vector space is braided by this abelian group A. And so to make it sort of quite concrete, to again sort of end on some picture of sort of viscerally seeing a fusion 2 category, let's just take A to be C2. Then this 4th cohomology group, you can sort of quite easily see is Z4. And so we have 4 different twistings that we can look at, and let's sort of just compare them to sort of end this talk on an example. Namely, I can take omega to be 0, so this is sort of the untwisted version. Then, as I've said here, this omega is 0 trivial, so this is just mod of vect C2. And mod of vect C2, well, you have a simple object which corresponds to your vect C2. And then you have a single indecomposable module, so there's a single other simple object. And this is sort of the semisimple 2 category structure. So you have this object X, you have this object I, and this is the semisimple 2 category structure, and this is the monoidal structure. I mean, there's more data to the monoidal structure, but this is, so to say, the fusion rule. So you have X squared is X plus X. If you take omega to be 1, you get actually just vect C2 twisted by some interesting monoidal structure already. So this is, even as a monoidal category is twisted, this is no other module. So this really has just a single simple object and a single block. And of course, then the fusion rules are also sort of obviously trivial. If I take omega to be 2, this corresponds to the braided fusion category, which is just super vector spaces. This is 2 simple objects. and this semi-simple structure. And in this case, the fusion rule is x squared is equal to 1. And then again, this last case is again one of these things. So, right, and they already see that there's from this sort of simplest possible example you can write down if you want of what multi-fusion 2 categories are. There's sort of quite a variety of different sort of phenomena appearing that are not very common for fusion 1 categories. So already sort of this twisting gives me sort of completely differently feeling semi-simple 2 category structures, and the fusion rules, as you can see here, don't look at all like fusion rules you would see for fusion 1 categories, like x squared is x plus x is definitely not something you would allow for fusion 1 category. And this all boils down to still have rigidity, this object still has a dual, and it's still self-dual, but it boils down to that you have interesting maps from x to I to x. So you can avoid a lot of sort of the restrictions you have on the fusion rules of fusion 1 categories. And I think that's the end of my talk. And so if you have some more questions, and I won't give this other example, but I'm happy to talk about this, some more examples. I definitely have at least one more example prepared, but I can also talk about unprepared examples in the
All right, wonderful. Let's, I think that we first thank the speaker. So I think we have time for questions. Anyone have questions?
In your last example, what are the conditions on the field K?
Right, so here I'm assuming it's algebraically closed and characteristic 0. Let's see, maybe, let's just say here I'm working over the complex numbers.
Thank you.
I mean, essentially what I'm computing is, since I just have a single component, I can just work in this braided fusion category that I have here, and I just compute essentially the Reutter category, the indecomposable separable algebras in there. And so in the S-vector example, of course, what one sees is that you have your trivial algebra and you have Clifford algebra and how they interact, and that this is sort of the fact that the Clifford algebra squared in supervector spaces is trivializable. So I think here I'm definitely working over the complex numbers.
Great, thanks.